The Space Telescope far in space, in an exoplanet known as the Next B, scientists with the help of the new and powerful James Webb Space Telescope are watching the light that can be the final solid proof that it is inhabited by aliens. And the scary discovery in the Next B by JWST. What a terrifying novelty to discover this masterpiece of engineering in the Next B. How it affects the chances of humans sending astronauts to this distant planet. Join us as we dive into the terrible discovery of the James Webb Space Telescope in the Next B that changes everything. Mars draws attention as the next possible planet to host humans, with Elon Musk from SpaceX in the vanguard to make it a permanent human base. Millions of miles away, Mars is relatively close to Earth, making it a possibility to send humans there, even if such a mission is a challenge. However, much further away in the universe is a class of planets that we will soon focus on one of them. They are known as exoplanets. What are exoplanets? Exoplanets are simply planets that orbit a star. What are exoplanets? Exoplanets are simply planets that orbit a star that is not our Sun. The prefix exo points to the fact that these planets are located not only outside, but far outside the solar system. Astronomers have confirmed thousands of exoplanets revolving around these distant stars and even more to be confirmed. The first two exoplanets were discovered orbiting a pulsar in 1992, and the first confirmed orbiting a star like a sun was in 1995. The discovery of exoplanets is thanks to the most powerful scientific equipment we have available today. Exoplanets like the Next B are difficult to detect due to various reasons. They are very distant, separated from us by light years. Another problem is that, like Earth, exoplanets do not emit light, but only reflect the light of the star they orbit. So, unlike their stars, exoplanets are very weak. Even the biggest ones are drowned in the light of their much brighter stars. That is why even the biggest ones are too small to be seen in optical telescopes. The discovery of exoplanets made scientists realize something about our own solar system. It is an exception in the world of star-planet systems. In fact, before we started to discover exoplanets, most scientists expected that exoplanets, if they existed, were similar to solar planets. But they found many different positions and orbits that are difficult to explain. There are several types of exoplanets, including hot Jupiters, called Tau because of their gas and mass content similar to Jupiter. Then there are super-Earths, which are planets with a mass between Earth and also the smallest gas giants, Neptune and Uranus, in our solar system. The composition of such planets is more rocky than in most gas, and that is why it is more likely that they are like the terrestrial planets Mercury, Venus, Earth and Mars. Some exoplanets are mini-Neptunes, with masses up to 10 times larger than Earth's. However, they are not as big as Neptune. Exoplanets containing a lot of water are known as ocean worlds, while ice giants are exoplanets that are volatile compounds like water, methane, and ammonia, instead of hydrogen and helium from Jupiter, also Saturn. A reason why scientists study exoplanets are to see if some of them can host life. Of all known exoplanets, none command as much interest as Proxima b, and the high level of interest will only continue with the new James Webb Space Telescope. The existence of the Proxima b was confirmed in 2016 and is located approximately in the middle of a habitable zone of the star Proxima Centauri. Its discovery was possible thanks to the High-Accuracy Radio Velocity Planet Searcher, or HARPS, at the European Southern Observatory. In La Silla, Chile, Proxima b star, Proxima Centauri is the nearest star closest to the Sun, only 4.25 light-years away. Scientists decided on the name Proxima b using the convention of names used by astronomers who found the planet. It has the name of the star followed by lowercase letters starting with B for the first discovered planet, C for the next found, and so on. You can ask about the planet closest to A, but the letter A is reserved for the star itself. One thing about the convention of nomenclature is that the order of letters is based on the order of the discovery and not on its distance from the mother star. How is Proxima b? The orbit of Proxima b is inclined towards Earth so that it does not make transit through the disk of the star. As such, scientists could not use the planet detection method of NASA's Kepler mission using blocked stellar light to see it. Instead, its existence was deduced from the oscillation of 11.2 days that it produced in the radial line of the star's vision speed while the planet orbited. At the time of the discovery, scientists discovered weak evidence suggesting a second planet, which proved to be correct. Proxima Centauri is a weak red dwarf star and has only 12.3% of the mass of the Sun. It also has only a 14.1% of its radius and only 0.17% of its liquid energy production. As a consequence, its habitable zone must be very close to the star. Like most small stars, Proxima Centauri is relatively unstable and is known to produce frequent large solar eruptions. Its temperature is quite low, 3042 Kelvin, compared to 5772 Kelvin for our Sun. Most of its emitted light is in infrared instead of visible. For this reason, it is so weak that even being close, you cannot see it in the sky, with the naked eye. The relative coldness of Alpha Centauri leads to the reduction of the support of its stellar material against gravity attraction, resulting in a very high density. The Sun has a density of 1.41 times greater than that of water, but the density of Proxima Centauri is about 56.8 times greater than that of water and 7.23 times greater than that of iron. A mass 129 times greater than that of Jupiter, Alpha Centauri has a diameter of only 1.5 times greater than that of Jupiter. The planet Proxima b is quite close to Proxima Centauri, only about 5% of the orbital distance from Earth to the Sun or 0.05 astronomical units. This means that it makes a complete orbit, or a Proxima b year, in only 11.2 terrestrial days. However, due to the very low energy output of Alpha Centauri, the average surface temperature of Proxima b is within the range in which water should be liquid on its surface. Proxima b is fixed in Alpha Centauri. What does this mean and what are the consequences? You probably know that the Sun and the Moon exert forces of tide over the terrestrial ocean. This type of force depends on the mass density of the object producer and the power of the angular size of the third object in the sky. Even for an observer on Earth, the Sun and the Moon seem to have approximately the same angular size. The influence of the tide of the Moon is triple the influence of the Sun because the Moon has 3 times the mass density of the Sun. Now, why does Proxima b have such a small orbital radius? The star Proxima b Centauri, even with its small diameter, will appear to have an angular diameter 2.86 times greater in the sky than our own Sunday. As seen from Earth, Proxima also has 40 times the density of the Sun. This means that the force of the tide of Proxima Centauri in Proxima b will be 939 times greater than exerted by the Sun over the Earth. So, it is most likely that Proxima b will remain blocked by the tide of Proxima Centauri. This means that, just as the Moon of Earth Proxima b, it will always have the same face as Proxima Centauri. The consequence is that Proxima b will have a hot side like the desert and a cold side frozen at the same time. But there will be a band of the twilight zone around its middle region, in which the star will always be just above or just below the horizon. In this region, the temperature will not be extremely hot or cold. But then, a tidy planet has its advantages. For example, if humans lived there, this means that solar energy farms would always generate electricity. Electricity will then be distributed to other parts of the exoplanet where it is necessary. Colonies can simply select a location with the average temperature they want and can hide from periodic solar eruptions, keeping the dangerous Proxima Centauri just above the horizon and out of danger. However, the colonies will have to deal with less sunlight. The light that humans can see, the visible spectrum, has a wavelength that varies from about 400 nanometers, 10 to 9 meters on the deep violet edge, to 700 nanometers on the deep red edge. However, the solar light of Proxima b reaches a peak of 950 nanometers, which is well within the infrared. It quickly falls in the visible region, with the visible light strongly inclined towards red. So, if the sunlight and Proxima Centauri b were equal on the red edge of the visible spectrum, the light of Proxima would be 10 times weaker on the violet edge. So don't expect to get a good tan lying on a beach on Proxima b. This, of course, will affect agriculture. Photosynthesis using chlorophyll works at maximum in wavelengths of about 470 and 660 nanometers and cuts to zero for wavelengths larger than 700 nanometers. So if you take plants from the Earth to Proxima b, they can be photosynthesized with just a small fraction of sunlight from Proxima Centauri. But there is an outlet to ensure that you receive fresh food continuously. The solar cells of silicon, which produce electric energy, have a peak conversion efficiency of about 700 nanometers and fall from 0 to 1100 nanometers. So, you can be able to do agriculture in Proxima b, putting large farms of solar energy, absorbing 700 nanometers of light on the hot side of the planet and cultivating plants in a stove, in a twilight zone illuminated by LEDs moved by electricity, producing wavelengths of 470 and 660 nanometers. But what about gravity in Proxima b? Just like the Earth, this exoplanet produces gravity. Proxima is at least 1.3 times that of the Earth. Well, it could be much more. If Proxima b is spherical, with a mass of, let's say, 1.5 terrestrial masses, approximately the same mass density as the Earth, the surface gravity of Proxima b would be approximately 1.145 g, or 11.22 m per second squared. So you push the scale to about 14% more than on Earth. But another variable that can change our calculation significantly. You see, the Earth has a relatively high density because of its nickel-iron core. However, Proxima b, like Mars, may not have a core like that. So, if because of that, Proxima b has the same mass density as Mars, or 3.93 g per cubic centimeter, the surface gravity of Proxima b would be 0.866 g, or 850 m per second squared. And you would weigh 14% less than on Earth. So Proxima b may not be spherical. The strong forces of the tides would tend to hit the planet with a closed tide, an ovoid shape, or even an egg, with a long axis, pointed at the star. Thus, any habitable zone would be located in the medium region of the ovoid, where its radius would be less, meaning that the habitable medium region would be closer to the center of the planet. Here, the surface gravity would be greater than in the hot and cold zones. If the radius were 10% less there, the gravity would be 20% greater. Proxima Centauri has frequent solar eruptions, and there is a debate about the resulting ionization that would take away any atmosphere that Proxima b could have. It has been argued that, if Proxima b has a core as fused as Earth and rotates in its axis every 11.2 days, this could be enough to generate a planetary magnetic field that would protect the atmosphere. Even if there is no native life in Proxima b, this could be an advantage. This is because many arbitrary points in the evolution of life could have resulted in evolution on other planets in a very different way than we have here on Earth. This type of alien life would probably be toxic to humans. Thus, for a colony site, a stereo planet could be preferable to a biologically hostile planet. Such pre-sterilization could facilitate the transplant of some simplified version of the Earth's ecosystem to Proxima b. Now, why are astronomers interested in the exoplanet Proxima b? To understand this, you need to know its location. Our nearest star is Proxima Centauri, located about 4 light-years away. Just like our Sun, Proxima Centauri has its own set of planets orbiting, one of the planets of Proxima b. This exoplanet was discovered in 2016 and has intrigued scientists since then. Scientists also discovered Proxima c and Proxima d, although Proxima d is still waiting for confirmation. However, much of the attention has been given to Proxima b for good reasons. Because the planet orbits right in the middle of its habitable star zone, it is possible that liquid water and potentially even life may exist there. Due to its mass similar to Earth, scientists believe that not only could there be liquid water in Proxima b, but it could also be a rocky and terrestrial planet similar to Earth. Proxima b orbits around a star that, although close to our solar system, is also much weaker and much less massive than the Sun. The exoplanet is arranged in synchronized rotation with its star, which means that one side is always facing the star and the other is always facing the other, one side light and one side dark. In addition, it is not clear if Proxima b has an atmosphere. However, if Proxima b has an atmosphere, the simple ingredients, water, carbon dioxide, and rock, which are necessary for the formation of biochemical cycles that we call life, could all be present and interact on the surface of the planet. The planet is very close to its star, completing an orbit every 11 days on Earth. The temperature on the surface of the planet could be between -90 degrees and 30 degrees Celsius or -30 degrees and 86 degrees Fahrenheit. Scientists are looking intensely for life outside this planet, but how exactly do they seek for life on these distant planets? Water is present in Proxima b. However, scientists do not know for sure the amount of water that Proxima b initially had, but their calculations have shown that Proxima b could have lost about 1 ocean of water due to early irradiation in the first 100 to 200 million years after the formation. What happened after that period is still under investigation. Perhaps this planet similar to Earth has continued to lose significant amounts of atmospheric gases or perhaps has been able to keep most of its atmosphere and preserve liquid water on the surface, making it a hospital for life. Scientists have even discovered where most of the water in Proxima b can be located, which would be useful if one day you could be stuck on the planet. By examining the possible climates using a sophisticated 3D model and exploring a wide variety of atmospheric compositions and water inventories, it was discovered that liquid water could be present on the surface of the planet in the most insulated regions, whether an area in the planet's hemisphere, in front of the star or in a tropical belt. If James Webb is able to detect the light from a narrow band that resembles LED lamps, it will be then how he will be able to characterize the planet's atmosphere. This will allow researchers to use instruments in the observatory to detect how much energy or transport occurs on the planet and then perform light curve calculations to determine whether they correspond or not to a LED light source. To reach the conclusion that he can detect artificial light, Loeb and colleagues used the JWST exposure time calculator. This tool allows astronomers to predict what can be detected in a certain period of time based on predefined settings before the launch of the observatory. It allowed them to determine the possibility of detecting different flux values and detecting those with a wavelength corresponding to the levels of artificial light that should be specialized in civilizations forced to live in permanent darkness. In this case, the lights that shine in permanent darkness must be extremely powerful and therefore more likely to be detected with JWST. The JWST will be able to show the existence of artificial lighting for LED standard 500 times more powerful than those currently found on Earth and for artificial lighting of similar magnitude to Earth. Of course, manned missions can be impossible, at least for now, but the Breakthrough Starshot project is trying to develop tiny nanoseconds that could go to 10 or 20% of the speed of light to visit the Centauri system. This mission is supported by Russian billionaire Yuri Munch. It may take decades for the probe to reach the next beat, but they will certainly help us discover more secrets about the exoplanet. When the Breakthrough spacecraft arrives at the next beat, will they find aliens waiting for them? It turns out that we have received signs of the next Centauri, which raises many possibilities. It all started with a strange signal captured by the Hipparcos radio telescope, 64 meters in Australia, and captured a weak signal while observing the next Centauri. The astronomers were using Hipparcos to capture the radio emissions of the powerful lightning shooting from the star. The detection was done for a $100 million project called Breakthrough Glucin, led by Andrew Simeon, from the University of California, Berkeley, and funded by the technological billionaire Yuri Munch, under the umbrella of the Breakthrough Initiatives of Munch. The objective of this several-year venture, which began in 2015 with the announcement of the star, with the presence of Stephen Hawking and other stars of space science, is to buy time for observation in radio telescopes around the world to search in the sky for evidence of technological civilizations. This search is most commonly known as the Search for Extraterrestrial Intelligence, SETI. Using Hipparcos, astronomers had observed the star for 26 hours as part of their stellar fire study, but as it is a routine within the Breakthrough Glucin project, they also signaled the resulting data for a subsequent search to search for any SETI candidate signal. The task is a young intern from Simeon in Berkeley, Shane Smith, a graduate student at Hillsdale College. Smith began to examine the data until he stumbled upon this curious narrowband emission, which dived to 982,002 MHz, and was hidden from the sight of everyone in observations of the next Centauri. From then on, things happened quickly. It is the most exciting signal we found in the Breakthrough Glucin project because we did not have a signal that has been stolen by these many of our filters before, says Sophia Sheikh from Penn State University, who helped in the subsequent analysis of the Breakthrough Glucin signal. Soon the team began to call the signal by a more formal name, BLC the Breakthrough Glucin, as Candidate 1. Although the press reports are not clear about exactly how and when Parkes detected the signal, apparently it appeared for 5 periods of 30 minutes for several days, all while the telescope pointed directly to the next one. Breakthrough Glucin uses a technique called head sinking, where the telescope will spend a period looking at a target, and then an equivalent period looking elsewhere in the sky to check if any potential signal is really coming from the target. In 5 of the 30-minute observations, for about 3 hours, we see this thing coming back, says Sheikh, a hint that the signal originated from the next Centauri, or some other source of deep space in that part of the sky, before making its way to Earth. Notably, when the telescope was diverted from the star, the signal disappeared. From the last analysis, the origin of the signal seems to be strongly restricted within a 16-wide circle, approximately half the size of the full moon, around the next Centauri in the sky. Breakthrough Glucin uses software filters capable of rejecting the cacophony of signals or terrestrial orbit satellites to isolate those coming from deep space, but this transmission was different from anything the project had previously encountered. Team leader Andrew Simeon told the Scientific American that it had some particular properties that made it pass many of its checks and tried to explain it, but curiously, it occupies a very narrow range of the radio spectrum, 9.82 MHz, specifically that it is a region typically devoid of satellite and spacecraft transmissions made by man. We do not know any natural way to compress electromagnetic energy in a single box in frequency, as this one says Samian. So, maybe, he says, something still unknown about plasma physics could be a natural explanation for the tempting concentration of radio waves. Now, talking about the meaning of Jason's discovery, a central astronomer from SETI at Penn State University, Pennsylvania, says that if you see such a signal and it is not coming from the Earth's surface, you know that you detected extraterrestrial technology. While the work is still underway to analyze the BLC-1 to confirm if it came from aliens, nothing prevents scientists from transforming the JWST into the next B. The interesting thing is that some scientists have tried to determine if the new telescope can detect artificial light, which is a definitive sign of civilization in the next B, working on the assumption that aliens on the exoplanet would use LEDs similar to those we have on Earth. Elisa Tabor from Stanford University and Eberlin Loeb from Harvard University concluded that if the night artificial lighting of the next B reached 5% of the daytime natural lighting, the JWST could detect artificial light with 85% certainty. In further research on the possibility of life in the next B, scientists also tried to determine what the Earth would be like as a planet, as it was orbiting the next centaur. They counted on modeling to find out what the situation would be like. Again, we go back to the concept of habitable zones. Just because the next B orbit is in the habitable zone, which is the distance from its host star, where water could accumulate on the surface of a planet, it doesn't mean it's habitable. They don't take into account, for example, if water really exists on the planet or if an atmosphere could survive in that orbit. Atmospheres are also essential for life as we know them because they allow climate regulation, the maintenance of a surface pressure favorable to water, protection against dangerous space storms, and housing life building blocks. The computer model used the magnetic field of the Earth's atmosphere and gravity as substitutes for the next BS. They also calculated how much radiation the next centaur produces on average based on observations from NASA's Chandra X-ray. With this data, the model simulates how intense radiation and frequent burning of host stars can affect the atmosphere of exoplanets. An active red star like the next centaur removes the atmosphere when the ultraviolet radiation of high energy ionizes atmospheric gases, knocking down electrons and reducing a range of particles charged electrically. In this process, newly formed electrons gain enough energy to be able to escape the planet's gravity and run out of the atmosphere. Opposed charges attract so that electrons with more negative charge leave the atmosphere and create a powerful separation of charge and pull ions with positive charge along with them out of space in the next centaur. The habitable zone next to B finds episodes of ultraviolet radiation hundreds of times greater than the Earth's dust from the sun. This radiation generates enough energy to remove not only the lighter molecules, hydrogen, but also, over time, heavier elements, such as oxygen and nitrogen. The model shows that the next centaur is a powerful radiation that drains the Earth like the atmosphere up to 10,000 times faster than what happens on Earth. To understand how the process can vary, scientists analyzed two other factors that exacerbate atmospheric loss. First, they considered the temperature of the neutral atmosphere, called the thermal sphere. They discovered that it has a warming of the thermosphere with more stellar radiation. The atmospheric escape increases. Let's hear what you think of life in the next B in the comments section below. Thanks for watching.